Okay, well, so then today we'll talk about regression models, and we have deviated from the syllabus, of course. We'll get back on track. I know that there's some folks that are interested in vegan and NMDS, non-metric multidimensional scaling in particular. I promise we are going to cover that stuff. I just wanted to make sure that we got through ANOVAs and regressions because those were two of the dominant responses that the class had given when I asked about particular analyses that you might want to conduct in R. So if you're just joining on Canvas in week 6, I've put an R file that's called regression_code.r. So you can download that and open it up. And I see Lindsay's asking, when you open this, the first thing you'll see is package RSQ, which is short for R squared, is not installed. We will be using that today, so you can go ahead and click install. And that's one of the nice things about RStudio is it recognized that I had library RSQ, but then it searched my library and noticed that that package wasn't there. And so it had offered to automatically install it. And if none of you have ever used that package before, you should see that same question and you can go ahead and install it, okay? And it might take just a minute to install that one. It's a package that's useful for calculating the R square, which is, if you've had a class, is the coefficient of determination, or how much variation in the Y or response variable is explained by the X or the independent or predictor variable. And so I'm just going to show you just one function from that package today. Okay. Everyone doing all right? So we'll start then with the same loading the library Ggplot, and it seems like that's working for everyone. And then the library car, and remember that is the companion to applied regression that we introduced last week. Okay, so you want to load those two packages. And remember, you can do that with the library function, or you can go down to this window and select packages and go down to it and click next to it. So car, I've already loaded, and notice it's got the little check next to it. Okay, and then we're going to keep, for now, for the time being, using this miles per gallon MPG data from the Ggplot package. So you can run that next little bit of code that's data MPG, and then it's MPG will load in your environment, and this promise is just, it's loading the data. It's eventually going to come up. If you were to click on that, it would automatically load the data. Okay, and the reason that we're sticking with MPG is just because we've invested a little bit of time in understanding what some of the variables in that data frame are, and which means that you're not having to simultaneously learn the data and learn the fitting of models. Okay, so we're going to stick with this just for today, so that you can focus on the code for the models and not necessarily what did the data represent. Okay, so the first model that we're going to fit is a linear model, and this is, if you'll recall from that flow chart that I introduced last week, the simple linear regression, or linear regression as it's called, has a number of assumptions that are required to fit that type of model. And so it's things like independence of the data, a linear relationship between the two variables that you're plotting, homoscedasticity or standardization of variances, and then a normal distribution of the data and a normal distribution of your residuals after you fit the model to the data. And remember, we always fit models to data, never data to the model. And so what I wanted to do today then is just start with a linear model, and let's fit it to some of these data that we've gotten to know. And then let's check some of those assumptions. And that's where we're going to be using some of these functions from the CAR package, the companion to applied regression. Okay, so I'm showing you how to fit a linear model. So we're going to call this model 1. And we're going to use this left arrow, which just means is equal to, or is defined as. And we're going to use LM for linear model. And notice those are both lowercase. We're going to use CTY, which is the city fuel economy, as the response variable. We have this tilde in there. And then we have displacement, which is a measure of the size of the engine. And that is our equation for the model. So it's city fuel economy as a function of displacement, which is a measure of engine size. And then we're just telling it the data are coming from NPG. Okay, it's starting out very simple, so we can fit that model. When you run that, notice we now have an object up here that's model 1. It's a list of 12. Because I named it model 1, we don't get any output automatically in our console, but we can just use this summary function as we learned about with ANOVA last week. You can remember when we fit an AOV model, we had to call summary of that, whatever we named that model, to see the results. And it's the same thing when you fit a linear model. So if we run summary of model, it's going to pull out the information that's in this list of 12 items here. And I'm just going to focus on this for just a minute, okay? So the first thing it does when you do the summary function, the call is just recalling the formula that we created. Here it shows you the residuals, and remember when we fit a model, it puts a model, in this case, a straight line through the center of the data, and then residuals represent how far each point is for each observation from the fit of that model. And so we get a median value, we get a minimum value, a maximum value. And we're going to think about, are those residuals normally distributed? That's one of the assumptions of a linear model, okay? But it tells you the distribution of your residuals. It tells you the coefficients of the model. So remember, the typical linear equation that many of you might have learned is y equals mx plus b, where y is your response variable, x is your predictor variable or your independent variable, m is the slope, and then b is the intercept, okay? And the intercept is where that regression coefficient, where the value of y at a, what I should say is where it crosses the y-axis, okay? At a value of 0 for the predictor variable. And then we have the slope related to displacement here. So we have a value of city fuel economy where if displacement were 0, so 25. And then we have this negative slope, which represents that it should be a negative or downward sloping model when we fit the model, okay? We can get an error for each of those, a t-value, and then a p-value. So this p-value is asking, does that intercept significantly differ from 0? And the answer is yes. And does that slope significantly differ from 0? And a slope of 0 would be a totally flat line. And what this is suggesting, this test here, is that negative 2.6 reduction in fuel economy as we increase a unit of displacement is significantly different from 0. It's not a flat line, it's a downward angle, okay? Then the 3 stars represents the level of significance. That's something that R supplies you. So 3 stars means that it's highly significant. If it were 2 stars, it'd be to 3 decimal places. 1 star would be to 1 decimal place, and so on. It gives you your residual standard error and the number of degrees of freedom. And then this multiple R squared, and if you fit multiple predictors in a multiple regression model, you might adjust that for the number of predictor variables. Notice those are pretty much the same thing. This is our coefficient of determination, or how much variation in city fuel economy can we explain if we have knowledge of the engine displacement, okay? And what that will always be scaled between 0 and 1, where 0 is no explanatory power, and 1 would be perfect explanatory power, a perfect relationship between the two. And so what this suggests is that there is about 64% of the variation in city fuel economy can be explained by the size of the engine, measured here as displacement. And then the F statistic is the measure of whether or not that is a significant regression model. And a larger F statistic or test statistic tends to be correlated with a significant model. And so the p-value for our overall model is very small, okay? Everyone doing okay with that? I know there's always kind of a mix of backgrounds among students in the class in terms of statistics and regression. And I wanted to start with just the basic model and give you a little bit of background on that and how to interpret the output that you get from fitting a linear model in R. Everyone doing okay? I'm just watching the chat and I don't see anything. Okay, so then let's check some assumptions of that linear model. Is that an appropriate model to fit to those data given the assumptions of the model? So this first function that we're going to use is called residual plot with a capital P. So residual is lowercase, but plot is a capital P. And this is from the CAR package, and we're just going to look at a residual plot from model 1. And so if we run that, what we get, and I'm just going to zoom in on this. What this shows is for the fitted value or the predicted value, how far are each of the points from that fitted line? And so these are what we refer to as residuals. The dashed line here represents a perfectly straight line, or a zero distance from each point between the line and each point. The blue line is a summary model or a summary fit of what our actual residuals look like. And so if we had perfect residuals, that all of these points here would be right on zero. What that would mean is the line goes perfectly through every point, and there's no difference between our observed data and the predicted data. But notice this blue line is not perfectly flat. Notice that there's some curvature to it, indicating that the residuals tend to be positive at small predicted values, and then they come down and there's a little bit of agreement, but then they become negative and then they become positive again. So this blue arched line or inverted arched line, curvilinear line going through there, indicates that we don't have perfectly homogeneous variance or residuals. So homoscedasticity, that assumption is violated here. We actually have heteroscedasticity. The residuals at small values tend to be positive. The residuals at intermediate values of the displacement tend to be negative. And then the residuals at very large values tend to be positive again. So if we had met the assumption of homoscedasticity, this blue line would be perfectly flat, and it would be somewhere around zero. It should lay right on top of that dashed line, okay? So then we can say residuals are curvilinear, not good fit for the nature of the data, okay? Then we can check for normally distributed residuals. So are those residuals centered on zero, and do they follow a bell-shaped curve? And to do that, we use the density plot function on model 1, but then notice we're drilling down into model 1 and we're grabbing the residual values, okay? So it's density plot, model 1, $ means what output from model 1? Well, we want the residual output from model 1. And if we run that, we get a distribution that should be something that you're starting to become more familiar with. This is showing across residuals centered on zero. This is a density function, but you can interpret it the same way as you might interpret a frequency distribution. So they do kind of follow a distribution that almost looks bell-shaped, but notice this tail is really long. Does anyone remember what kind of skewness we called that? Right skewed or positive skewed. Very good. Yeah. So notice the tail's going very long in the positive direction. And then notice that there's this little dip. It's not a perfect bell shape. It's almost like there's two peaks there. So bimodal almost. Not what we would expect to see in a normal distribution. Okay. So this is all just thinking about after we fit that model, what do the residuals look like on that fitted model? There's one more assumption we can test for, and that's this assumption of independence, that the observations of displacement across all of the data in our data frame are independent of one another. And if they are not independent of one another, then we violated this assumption of independence. And to test that, it's the Durbin-Watson test, where Durbin is D with a lowercase d, Watson is a capital W, and test is a capital T. And notice now we're just doing that test on the model that we created. And if we run that, this gives you a lag, an autocorrelation value, a test statistic, and a p-value. And what it's testing for here is whether or not there is a significant level of autocorrelation in the model. And so our p-value here shows that that's a value of 0, so a very small value, a significant value. That suggests that there is a significant existence of autocorrelation, meaning some of those observations are more related to each other than others. Okay, that's what that means. And it tells us our conclusion there, the alternative hypothesis, that this rho value or this autocorrelation value is not equal to 0. So the exclamation point equal sign means not equal to 0. This autocorrelation value here is significantly larger than 0. And what that means is some of the observations are more closely related to each other than other observations, okay? So let's just plot this model using Ggplot, and hopefully all of this will make sense. Okay, if it's not making sense, let's think about it from a visual perspective. Okay, so I'm going to use Ggplot. We're going to tell Ggplot that we're creating data plotted from MPG, and then we're going to map the aesthetics. So the aesthetics means what do we want to show? So we want displacement on the X and city on the Y. Inside of AES, it's always X then Y. Then we're going to tell it what type of plot we want it to create. So notice when we give this argument, we could create any type of plot we want. We're going to create a point plot or a scatter plot. So it's GM_point. And then we're going to fit a smooth to that like we were learning in the last week. Here we're going to use method equals linear model. The formula is Y as a function of X. Okay. So as we fit these again and again, I want you to be thinking about what are the arguments that we're giving Ggplot to make a figure. All right, so we run that, and here's our plot. So I'm going to zoom in on that. So here's displacement on the x-axis. That's a measure of engine size, and here's city fuel economy on the y. And then this blue line is our linear model that we fit to that. So remember, we had an intercept. That's where this line, if you follow it out, and we went all the way down to a displacement value of 0, what would the value of city fuel economy be? And that's where we had that value of 25. That's our intercept. If you follow this out to x value of 0, where does it cross? That's the intercept. And we had tested, does that significantly differ from 0? So it's way up here around 25, not at a value of 0. But most of the time in regression, we're more interested in, does the slope differ? So as we increase engine size, as displacement increases, notice that there's a reduction in city fuel economy. Okay, so we have a negative slope here. For every unit increase in displacement, we have a decrease in city fuel economy. Okay, so this is that negative slope. Notice it's going downward. And if it were a positive slope, it'd be going the other direction. It'd be going from upwards from left to right. Okay. So then we were able to fit the model. We were able to explain about 64% of the variation in city fuel economy using this engine size. But remember, our residuals were not standardized. It was not the same error in the model across all of the fitted values. And the way that plays out when you look at the fitted model is, notice this observation here is much higher than the predicted observation here. And this observation here is much higher than the predicted value here. These are closer. This one is very close. We predicted value is pretty close there. But notice in general, these are all positive. The model under predicted city fuel economy for these low displacement engines. And then as we go in, and then as we increase displacement, notice a lot of these tend to be negative. We are over predicting. And then as we go out here to really high displacement values, notice we're again under predicting. These residuals are positive. And so that's when we compared that dashed line and then had the curved line going through it. That's what it looks like when you actually look at the fit of the model. These are all positive, these are generally negative, and these are all positive. And what that means is we do not have a uniform distribution of residuals. It's not a bell-shaped curve. There's that long tail for these observations that are way out here that are very positive. And then there's negative values, but they tend to be closer towards the actual value. Okay. So what those functions are doing when we look at homogeneity of variances or homoscedasticity, and we look at normal distribution or the distribution of the residuals, it's just thinking about or showing us information about how far each of these points are from that fitted line. Okay. And then when we did our test for independence, notice that when we plot these data for a single value of displacement, we get 1, 2, 3, 4. There may be multiple points stacked on top of each other, but notice they're perfectly vertical. These observations are not independent of one another. And probably what it is that these are different drive types or transmission types or manufacturers. So those displacement values are not totally independent of each other. It might be the same engine, but put into different options according to the data that we have, okay? So that's why we have violated that assumption of independence. Anytime you see multiple observations within the same value of displacement, that's an indication that those observations have some sort of autocorrelation to them, okay? Is everyone doing okay when thinking about these assumptions of a linear model? What we're going to work through next is I'm going to have you think about a slightly different model, and then use some of these functions that we've just gone through to think about whether or not that model is a good fit to the data. Okay. So your first challenge, and we'll just kind of do this in real time. I'll hang out while each of you work on this. I say, well, that was a terrible model. And I can say terrible because we've quantified that. It doesn't have homogeneous variances. It doesn't have a normal distribution of residuals. It doesn't really fit the linear relationship. Because if you just look at the data, you notice that it's kind of curvilinear. It's not a linear relationship. And we violated the assumption of independence. So all of these core assumptions of a linear model have been violated by these data. So I say it's terrible in that we should probably be fitting a different model. And that's what we're going to do as we move through this. But first, what I want you to try to do is to modify the code that I've given you and assess whether or not the model for the relationship of highway fuel economy as a function of city fuel economy is any better, okay? And then I want you to test whether the residuals are homogeneous. Are the residuals normal? And then can you create a plot, okay? So take a bit of time to work on that. If you have questions, we can either go into a breakout room or you can ask in front of the entire class. If anyone wants to share their screen, I'll make it possible for you to do that. But challenge yourself to create a model where you have highway fuel economy as the response and city fuel economy as the independent or predictor variable. Okay, and let me know if you run into problems. And what I would do if I were you is just start coding right below this challenge 1. Just build your model right there, and you could call it answer 1. And that way, after you do this, you can save this regression code in R, and you can send that to me as the output from your coding challenge today. Okay, so just work within the same file that you downloaded. Has everyone had time to come up with a model? Anyone struggling with that part? Okay, so we want to create a linear model, right? Hopefully this is the direction everyone went. What's the response variable here? We want it to be highway as a function of CTY, and the data came from MPG. Is that what everyone else did? Okay, so we can fit that model. And then we want to think about, what did I ask you for? Are the residuals homogeneous and are they normally distributed? So of course you can just reuse residual plot and density plot. The car package, and then we just tell it answer 1. And what's the answer? What's our conclusion from this plot?
It's not homoscedastic?
Yeah, very good. Yeah, it's closer compared to the other one. If you look at the magnitude of those residuals, we're within 4 most of the time. But notice we're still overestimating here. We're doing a little bit better, but then there's these kind of points out here that are underestimated. And then in the middle, that's generally pretty close agreement, okay? So it's closer, but it's still not a perfectly flat line, okay? So there'd be a few things you could do here. You could either choose to remove these outliers and fit the model again. Of course, if you ever remove any data, you have to be very transparent about that. You have to tell your readers why you did it and how you did it. But ultimately, what it looks like is we still are dealing with a curvilinear relationship instead of a linear relationship, okay? Good, okay. And then what was the other plot that we were gonna do? Density plot. And then if I just run this, will that run, or is there?
Residuals.
Yeah, we want to just grab the residuals for that. And I typed the wrong thing. So remember when you do the $, we could grab the coefficients, the residuals, the effects, but we want the residuals, and we can plot that. Okay, and what's your interpretation of that distribution of residuals? Pretty normal. Okay, pretty normal. It looks like a bell, maybe, right? But is it skewed in any way? Anyone on Zoom, does that look skewed to you? And if so, what direction?
It looks a little skewed to the left.
Okay, yeah, it might be naturally skewed. Certainly that tail is longer, but the tail on the right is thicker. So of course we could, based on our goodness of fit tests that we learned, we could compare that to a normal distribution. But it looks like it's non-normal to me. Yeah, very good. But it's close. So that's the thing about regression models is, you know, you can transform the data to approximate a normal distribution. You can still fit the model, but you just need to be transparent about the fact that maybe that's not perfectly distributed. And if we go back, it's because we've got some large negative values in this direction, and then a large number of closer positive values that are causing this tail to be a little high. Okay, so and then plot it. Okay, so if we want to plot that, and let's go through this without copying and pasting, because I know Ggplot takes a little bit of time. But so remember, Ggplot, and I hope you challenge yourself to do this. We're still going to plot the same MPG, but here we're going to tell it that we want highway on the Y. On the X. Is that what you guys did? Caitlin, did you want to say something?
Oh, sorry, I didn't realize my mic was not muted.
Yeah, okay. No, that's fine. Anyone, everyone doing okay here? So what's the next thing that we add? Because there's two things that we're doing, right? We're doing a scatter plot and then we're fitting the regression. Yeah, geom underscore point. And then we can do geom underscore, I think we just did smooth before. Just going to hit enter so it all stays on here. And then we did method, right? We're doing still a linear model. And then we can give it the formula. And is that in quotations? I can't remember.
Wasn't.
So method, because it's a name, you'd want to put that in quotations, but you don't have to put the formula. Okay.
Price was still X then Y under aesthetic.
So under aesthetics, we want, yeah, that's right. We want the X and then we want the Y. Very good. And then in the formula, it's Y as a function of X. Okay. Good. Did everyone else catch that? When you're giving the aesthetics arguments, it's always X and then Y. Very good. Okay, and I forgot to do something. I misspelled the name of it's mpg miles per gallon. Okay, there we go. So now, what's the first thing you notice about the slope of this model?
Positive.
It's positive. Very good. Yeah, and if we wanted to get more information on that, we could do summary of answer 1. If we run that, and we look at it side by side, here's our intercept. Notice that intercept's very close to 0. If you were to follow this out down to a city fuel economy of 0, it's going to be very close to 0. And in fact, it does not significantly differ from 0 if we use the conventional 0.05 as the cutoff. Anything less than that would be significant. And notice R is giving you just a single dot there, representing that it's what some interpret to be marginally significant. But you kind of have to be careful with that because some statisticians, the classically trained statisticians, see the world as black and white. It is either more or less than 0.05. In our case, it's more. So they would say, cold hard, that is not significant. But in an ecological sense, sometimes we recognize that, hey, that's pretty close. That's on the borderline of maybe being slightly higher. Okay, and then the slope, as someone pointed out, is positive, and that is significantly positive. Okay, everyone's comfortable with the idea of intercept and slope because we just build on those ideas when we create these more complex models. Okay, and so you can kind of see there's all of these positive residuals that are right here, and then that kind of goes negative. That would be why our distribution was a bell shape. It didn't have the bimodal part like the first model did, but it still got a little bit of skewness to it. Okay, and then did anyone test for autocorrelation, or can anyone guess what we would find if we did?
There were some points that were correlated.
Yeah, notice we still got these perfectly stacked data representing the fact that those are identical values means that they probably have some autocorrelation. They've come from maybe different manufacturers or different transmissions or different drives. And that's where, remember when we were talking about that flow chart, if we violate independence, that's when we move into a mixed model. And we're going to go over that in a minute. But first, let's talk about what we can do to deal with the fact that this is not a linear relationship, that it's a curvilinear relationship. And that's where we go into the realm of generalized linear models. So we're not assuming that the error distribution is a bell-shaped curve or a Gaussian curve. Okay. Before we do that, are there any other questions about the the linear model that we fit? Everyone okay with those concepts? You're able to do it? Okay, then let's move on. So model 2 here is just what we're going to call this. And notice now that we've changed the function that we're using. We're no longer using LM, we now have GLM. And a generalized linear model is where we're relaxing the assumption of normally distributed data, okay? So notice I'm going back to fitting this model that I had fit earlier, where city fuel economy as a function of displacement, but now we're changing the family. And that's in R, when you're fitting these models, the error distribution, they call it family, okay? So we could do different types of families here. If we did the binomial error distribution, the binomial family, that's, as the name suggests, two outcomes. What kind of model would we be fitting if we only had two outcomes and we fit a generalized linear model? Does anyone know what the other name for that is typically called, or it's a yes or no outcome? It's not we can think about a probability distribution between the yeses and nos, but there's a different name that's used for that, where you have maybe a 0 or a 1. Has anyone ever fit a model like that or thought about that? Maybe you've heard of logistic regression before. Yes or no logistic regression. So you can fit a logistic regression. So like in my lab, when we're tagging fish, we want to know what's the smallest size fish we can put a tag in without killing it. And so we have fish size on the x-axis and live or dead on the y-axis. And if it lives, then it survives. But if they die, and it's usually towards the smaller size, we might want to think about the probability of dying between 0 and 1 as the size of the fish is reduced. So logistic regression you can fit. With the GLM, you just need to have a response variable that is a yes or no, or two classes, and then some continuous predictor variable. Then you would just change the family argument to binomial. And you can do question mark GLM to learn about this. And so in the stats package, fitting generalized linear models, family Gaussian, the default is actually what linear models assume, okay? So we're typically not fitting that family. We're going to go to these different families. We're thinking about binomial. So then you would put, in place of family equals Poisson, link equals log, you would just put this whole thing, binomial link equals logic. And this link part, I know you wouldn't have been able to predict that, but that's just basically how R interprets the data. When you want to fit a binomial in R, you always do family equals binomial link equals logic, okay? Gaussian is link equals identity. And then we're doing Poisson. A Poisson distribution at a number very far from 0 is a normal distribution. But as you start to push that value towards 0, it starts to become skewed positively. And the whole point of using a Poisson error distribution is to acknowledge the fact that you may not have observations that can be less than 0. Okay, and certainly fuel economy can't go less than 0. So at Poisson, it's a normal distribution when you're thinking about really large values. But then as you move towards 0, it starts to skew the data so that the data don't go below 0. And what that turns into is a curvilinear relationship as you're coming down, in our case, in fuel economy, and then you start to, you can actually start to level out a bit, okay? And so what that means is if you look at the plot of the residuals, and we can do that, is they will be positively skewed, okay? That's a Poisson distribution. You can do a quasi-Poisson with more sophisticated models if you go down the rabbit hole of generalized linear models. There's a lot of other families that you can fit there, okay? But I just wanted to give you guys an indication of how you would fit these models. And of course, if you develop your own data and you want to fit these, I'd be happy to help you make decisions about which error distribution to use, okay? But for today's purposes, we're just going to try this Poisson. And we're just using this exact argument that I got to by going to the help, the internal help structure for GLM. So I just typed in question mark GLM. Then I went down to family, and it says see family for details of family functions. I clicked on that, and then it took me here, and that's where I found this, okay? So if you're ever later fitting a generalized linear model, that might be helpful. Okay, so if we were to do family equals Gaussian, link equals identity, it would give us the exact same model that we just fit with the LM argument, okay? But we're gonna change the error distribution to a Poisson. Everything else is the same, okay? Inside of the arguments here. And then of course the function, we put this G in front of it. Okay, so we can fit that model. And then we can look at the summary, just like we did for model 1. And so here we've got the call. It tells us the deviance of the residuals. It gives us our coefficients just as it did earlier, our intercept and the slope for dispersal or displacement. And then it tells us the significance codes there. It tells us a little bit about the null deviance and the residual deviance. And then it gives us an AIC, which is the Aki-Iki information criterion. And later on in the semester, we'll talk about how we can compare models with different variables in there using the AIC. Okay, so we'll come back to that later. But the important thing is that it gives you an AIC value for every model that it fits. Okay. But notice what's missing. We don't have the R² value in there. And because it's a Poisson distribution, it's a little more complex to calculate that R² value. And so that's where we're going to run library RSQ, which we installed when we first opened this file. And then the function is R² on the name of the model that you just fit. And if we run that, we get a value. And notice now we're explaining about 68% of the variation in city fuel economy based on the size of the engine, in this case displacement. Okay. So it's a little bit better fit, and we can go in and actually plot it and see what that looks like using Ggplot. So this first part hasn't changed. We're still giving it the data that we want to plot. We're still telling it the aesthetics, where it's the X value and then the Y value. We're still doing geom point, but notice we've changed geom smooth. The method now is equal to glm. The formula here hasn't changed, but method.arguments change, and now we can tell it this inside this list, the family that we want to use. Okay, and this is in Ggplot, you only need to tell it Poisson. You don't have to do the link equals log as you do when you're fitting a GLM. So this is the stats package. This is the Ggplot2 package. So there's a little bit of difference between the two. But if you take the time to learn to plot it in Ggplot, you can create a much better plot than just the very basic plotting package. Okay, so I'm going to plot this one, and then we'll have a look at it. And what I want you to notice is the first thing, that we're now thinking about a curving line. Notice that as we start to go down to a city fuel economy closer to 0, that line starts to flatten out. And if it went all the way down to 0, this line would hit 0 and then it would go right along the 0 line. It would not go down into negative, prediction of negative fuel economy at a really high displacement value, okay? And so this curvilinear fits the data a little bit better. We're getting better in terms of the distribution of the residuals. But can anyone tell me, like, do you think we have standardized residuals even when we fit this curvilinear model? And I see some people shaking their head no. And hopefully what they're looking at is the same thing everyone else is looking at, is that these residuals all still tend to be positive. There's a few more there that are negative, but these still tend to be positive. And if we were to do the same sort of plot that we did earlier, so I'm going to close this. If we did the, let's do the density plot, for example. And let's do it now on model 2, right? Residuals. Notice that we still have the same kind of binomial or not binomial, but these two peaks here, right? So it's a little bit better, and then we could use the other plot that we used earlier, which was the residual plot. Here. And if we run that, notice we're doing better now. With this curvilinear model, the magnitude of the residuals is smaller, and now it fits a pink line instead of a blue line, but we're still comparing the colorful line to the dashed line. And notice that we're doing a lot better at the higher levels, but we're still have these positive residuals here, okay? So by fitting a different error distribution, we've improved the fit of the model. The residuals are almost perfectly flat. And that's reflected in a higher R-squared value, right? So we saw that our R-squared value had increased to 0.67 from 0.64, which means that these points are coming closer to 0. And remember, if this was 1, a perfect correlation, all of these points would be on 0, okay? So challenge 2 then is to have you think about the relationship between displacement and highway fuel economy. Is there a better fit if we think about the response variable not being city fuel economy, but highway fuel economy?
My RSQ package is not working, and I'm afraid to try and download it a zillion times and have a problem like I did with Ggplot.
Oh, yeah. Is it giving you any sort of error message it does try to download it?
Yeah, whenever I went to run it, it said there's no package called RSQ, even though I had downloaded it before. And then it says,
Did you install it at the beginning when I clicked it? And what did it say at the end there?
I thought it installed, and then I guess it didn't, and I scrolled back up and there's nothing there. And so then I went to install it after it came up with the thing that said there's no package. And then it said, RTools is required to build R package, but is not currently installed. Please download and install appropriate version of RTools before proceeding.
Okay. Okay. So this is the same issue we were having with Ggplot.
I don't know if it was the same.
What I mean by same, that is when you try to install packages, it does not work on your machine, and it may be a larger problem related to RTools. Last time we had just installed Crayon and it worked a lot, but maybe it's an RTools issue. Okay, are you okay with us handling that outside of class? We could do it via Zoom. I know you drove here last time to get it fixed.
Yeah, that's fine.
Okay. Sorry that it's continuously giving you. I know this is like the best way to turn someone away from R, is for it to always have problems like this.
Well, hopefully next week I can get my new computer from A&M, and then it'll be fine, and I'll just start over.
That might solve your problems. Okay. Well, if it doesn't, let's meet one-on-one, and we can do that via Zoom to make sure you can install R-squared.
Okay, thanks. I'll just watch and listen in then.
Yeah, the only thing you're going to be missing today is just this added way of thinking about fit for the model. So we're only getting a couple more lines of code. But Ggplot's working okay for you?
Yeah, I haven't had any problems with that. So that's fixed.
Cool. Okay. Was everyone else able to do challenge number 2 there? So you could just call this one answer 2, and we're thinking about highway now. And we could have a look at some of these. One of the things you can do is just go Control F, and we can find, and we're going to find model 2 just within that selection. So I selected that, and we're going to replace that with the word answer. And if we place all, why did it not do that? Oh, 2 occurrences. Okay. So there, notice it found it and changed it for me. I'm going to close this all. I just found that by, or brought that up by doing Control F, by the way. So we can do the density plot now. Oh, oops, I forgot to do replacement with answer 2. So there's our density plot, and then there's the residuals. And it's pretty close, right? I mean, this is definitely a better fit with the generalized linear model compared to the linear model, right? But what about do we still have any issues with autocorrelation? So we can go back up and grab this bit of code. Oh, wait. Put it right here. And we'll just run that code on answer 2. Okay, and remember the Durbin-Watson test is testing for autocorrelation, and notice that we still have violation of this assumption of independence. There's some autocorrelation in there, related again to the fact that there's these stacks of points in here that are coming from observations of the of city highway or city fuel economy that come from the same value of displacement. And that's where we need to use a generalized linear mixed model, or generalized linear mixed effects model, to account for this non-independence or autocorrelation that's still present in the model. Okay. Is everyone ready to move on to this third part here for generalized linear mixed model? This is the we'll do this, and then there's only just one more coding challenge after that. Okay. All right. I see head shaking and thumbs up, so we'll keep going. So to fit a generalized linear mixed effects model, or even a linear mixed effects model. Remember, you could do a mixed effects model where you have a Gaussian distribution. We use the package linear mixed effects 4, LME4, okay? And so you may have to install that, but I'm gonna run that. And actually, Caitlin, I'm interested to know if you're able to load packages like LME4.
Okay.
If you'll try that one and see if you get that same issue with our tools. And hopefully everyone else can install that one and then run library on LME4.
It says successfully unpacked.
Okay, so that one worked. So then
Yeah.
if you run library LME4, it comes up okay?
I got a warning message, but I think it's all right.
What's the warning message say?
Warning message package LME4 was built under R version 4.0.4.
Okay. Okay, so that means that you're using an older version of R.
But we checked that I was updated like 3 times.
Yeah. Okay. Okay.
Used.
Well, you and I will keep working on that. And then when you get your new computer, of course, once you install everything. But
Okay.
typically that warning message, just for everyone, typically you get that message if you install a package that was developed under a newer version of R than what you are using. Okay, is everyone ready to keep going? Okay, so now we're moving into the realm of generalized linear mixed effects models, and this is where we have fixed effects and random effects. And a fixed effect is the effect that we're typically interested in. So here we want to know something about displacement and its influence on either city fuel economy or highway fuel economy. But we may have these random effects that we aren't necessarily interested in, but they're creating this autocorrelation that occurs in the model. And so this might be things like the identity of the manufacturer of a vehicle, or it could be that the drive type or the transmission type or the model of the car are causing this stacking of the data where there's multiple observations of the same displacement across these different classes of data. Okay, and so we might want to account for that in our hypothesis testing and our model fitting, but we're not necessarily interested in whether or not those mixed or those random effects are significant or not. Okay, so that's the whole concept of a linear mixed effects model. We'll have fixed effects and random effects. We want to know something about the fixed effects, and the random effects, sometimes you'll hear them referred to as a nuisance variable, or a variable that we want to account for in our testing, but not necessarily draw much inference from it. Okay, so if you're able to run library LME4, the main function that we use here is GLMR, so Generalized Linear Mixed Effects Regression. Okay, that's what the GLME are, and that's the function that we're going to use. And there's some subtle differences beyond that, but really not. So by the way, you could run LMR, which would be linear mixed effects models. If we had found that the normal distribution of the assumption was met, and we didn't have to fit a Poisson model, we could just do a LMR. But in this case, we want to retain that family Poisson in our area distribution, because we did find that there is an improvement in the homoscedasticity assumption when we use this generalized model as opposed to the linear model. Okay, so we're going to use GLMR. We're still got city in this case as a function of displacement, but now we're adding this little bit of information that represents the random effects in our model. So here we're going to do one pipe delineation. So that's for, on most keyboards, that's shift in the key just above the enter on the far right. Okay, so we've got one pipe delineation, and then whatever the random effect that we want to include. In this case, we're going to see if it's different manufacturers. Maybe there's two manufacturers that make the same displacement engine, but they might get different fuel economy because of other things related to manufacturing. And it could be that we've got the same engine size across different manufacturers that we want to account for there. Okay, so we're still using data from MPG, and then notice we're still using family equals Poisson, link equals log, the same thing we were doing when we fit the GLM earlier. Okay, so we're going to a new package, we're using a new function, but notice this function is built using a lot of the same kind of syntax that we saw when we were fitting linear models and generalized linear models. But now we have the added benefit of being able to put in our fixed effect, which is displacement, and then our random effect, which is manufacturer. And what we're saying is that we're going to allow the relationship between displacement and city to vary across different manufacturers. Okay, so if I run model 3, hopefully everyone's able to do that. We can have a look at model 3. And we're going to get a little bit more information now because we're doing a generalized linear mixed effect model, still based on maximum likelihood. That's what the others were using. The family here is Poisson, so it's telling us what part of the general statement there. So instead of Gaussian, we're using Poisson. It tells us our formula, it tells us where the data came from. There's the Akiyuki information criterion. Then there's the Bayesian information criterion. These are both methods for comparing different models that we'll talk about later on, okay? But just know that the Glimmer function automatically calculates AIC and BIC for you. It tells us something about our random effects, in this case, manufacturer. So we're letting the intercept change according to the manufacturer. It tells us the standard deviation there, the number of observations, and then the number of manufacturers. There's 15 different manufacturers there. Then we get the fixed effect, the part that we're interested in this case, engine displacement and its effect on city fuel economy across these different manufacturers, okay? So a lot more information coming out of this now, including information about random effects that we want to include in the model, and then fixed effects that we're most interested in testing, okay? And so we can calculate the R square. So Caitlin, this won't work for you because that we'll figure out why that package is not loading, but you should be able to get for the model, and that's including random and fixed effects. And then what we're really interested in is what is the explanatory power of the fixed effect. And now notice we're explaining a little bit more of the variation, the 67%, using this model that also includes random effects, okay? And I know mixed effects models for some of you may be more complex than what you're accustomed to dealing with, might be a little bit outside of your comfort zone, but I wanted to create a plot for this that might help you to understand what is actually happening here, okay? So we're gonna use Ggplot again, MPG. We have the same AES argument, so the x-axis and the y-axis. We're still doing the same scatter plot. We're still doing the same geom smooth as we did in the previous generalized linear mixed effects model, where we're using method.arg for family equals Poisson. But notice I'm adding one more thing on here. I'm adding facet grid as the function. And then we're going to make each of those plots according to the manufacturer. So we do the little tilde symbol, and then we tell it manufacturer or basically the identity of our random effect. And what Ggplot will do now is create a plot window for the relationship between displacement and city fuel economy, but it's going to do it by each manufacturer. And if we plot that, it's a very complex looking plot because there's a lot of panels in there. So we'll zoom in on this. But notice now we have this relationship between displacement, city fuel economy here for Audi, for Chevrolet, for Dodge, for Ford, for Honda. And notice that we don't have the multiple observations stacked for displacement. Different manufacturers may offer the same size engine, but now we've split those out by the manufacturers. And you notice it's the same general relationship, but some manufacturers tend to offer a larger number of small displacement engines like Nissan. Some manufacturers like Toyota offer a lot of different options in engines. Some like Volkswagen tend to be small, low displacement. Others like Mercury are in the middle, okay? So when we include manufacturer as a random effect, what the model is basically assessing is, does the nature of that relationship differ across these different manufacturers, and does that account for, or does it appropriately handle this issue of non-independence or autocorrelation? Okay, so here observations on the relationship between displacement and city is being treated as independent from Dodge for Ford. And so we're actually accounting for this non-independence by putting this random effect in the model, okay? And that's why mixed effects modeling is the route that you go when you violate the assumption of independence, okay? Because you can account for that non-independence with random effects that you introduce into the model. Okay, we'll just close this. And the last little bit is then, can you fit a generalized linear mixed effects model with fuel type as the random effect, and city fuel economy as the response variable, and displacement as the fixed effect? Okay, so I'll give you just a minute to work on that, and that's the last challenge for the day. The last thing that we'll cover then is this generalized additive model. But so what you are hopefully picking up on is that it's just a matter of understanding the model structure but here, because I asked you to use fuel type FL as the random effect, you just have to change that one argument, and then we can change this to answer 3. Run that, the model fits okay. You can do the summary function to learn a bit about the model. And I'll just plot it for you because we're coming up on the end of class time here. And I'm just going to change this facet grid to fuel type. If we plot that, now we can zoom in. And notice now that, and I don't remember what all of these fuel types, there's petrol and regular. So this is a diesel motor. This is a regular gasoline. I think this is ethanol. I don't remember what these are. But notice though, because we don't have as many classes here, there's a lot of non-independence for regular fuel or diesel fuel. So this may not be the most appropriate random effect to include in the model if we're interested in addressing this issue of a lot of non-independence in these observations, because a lot of these manufacturers offer regular fuel. Fewer of them allow for diesel, but notice we still don't have the most appropriate decomposition of non-independence, okay? Okay, and then if that still doesn't work, if you still can't adjust for non-independence using a mixed effects model, the ultimate, most complex model is a generalized additive model, okay? And I'll just show you how to fit this, and then we'll be done for the day. But to fit this, we've got this library MGCV is what's used to fit generalized additive models, okay? So you should be able to install that and then run the library function, okay? Then to fit a generalized additive model. So here, generalized represents the fact that we're no longer using this Gaussian distribution. And then additive model represents the fact that we're going to plot the data, but we're going to use this moving window across the data. And we're going to, as that window moves across there, it's going to fit the most appropriate summary of the data. And then as that window moves along, you get this very smooth function. So it's a lot like a Logistic Regression, a generalized additive model, because you can deal with autocorrelation, non-independence in the data. You can even do a generalized additive mixed model if you want to put a random and a fixed effects in there. And the only thing you really have to change, it's GAM as the function, city as a function of displacement, but we're going to use the S to represent a smoothing factor for displacement. Okay, so we're going to move across the gradient of displacement, and we're going to fit a smooth regression that explains variation in and city fuel economy. Okay, and the data are still coming from MPG. We can run the summary of the model. It gives you an adjusted R-square value here. So now notice now we're explaining about 73% of the variation in the model. And if we plot that, to plot that in Ggplot, you just got to tell geom smooth that you want to fit a GAM. And then you just change the formula to include that smoothing function. And if we run that and have a look at the output, notice now the model fits the data remarkably well. We've got this nonlinearity that's happening here. We still might want to include a random variable in there to get an autocorrelation, but notice that the data are a much closer fit, and this is because we're essentially drawing a box around these data, fitting a mean, moving the box to include these data, fitting it, moving the box to include these data, and just working our way across the gradient of engine displacement to create a model that is a really nice fit to the data. And of course, the downside is we can't interpret there's not a set slope here like there is in a linear model or a generalized linear model or a generalized linear mixed effects model. You basically have to show the relationship, and you can't do much prediction outside of the data that you've observed here. So we wouldn't be able to make any sort of prediction outside of displacements that are greater than 7 or less than this 1.5 here, okay? So there's some, and then the other thing is you need a lot of data to fit a generalized additive model there. But if you were to run the plots to look at the distribution of the residuals there, it's going to show a much flatter line there because the model is following the distribution of the data. Okay, so that's getting into pretty complex model fitting in that case. But some of you may have to do that. You may have, if you go all the way to a generalized additive mixed effects model, a GAMM. That's where you have violated every assumption that linear modeling has. Okay, so that's as complex as it's going to get. And I showed you GAM model, but there's a GAMM4 is the package if you want to create generalized additive mixed effects models. Okay, and I'm certainly happy to help you, anyone that wants to fit those outside of class. I didn't want to. I didn't think we'd have time, and we did not have time to cover all of that. But if that's something that has piqued your interest and you want to come back to it, we can make time for that in the course of the rest of the semester. Okay. I know some of you have to go. Our class time has ended. I've recorded this. I'll put it on Canvas for those that had to miss today. And then we'll pick up next week with the vegan package. So that's what we had pushed back in the syllabus. I want to make sure we spend time on that. In particular, it sounds like non-metric multi-dimensional scaling is one of the vegan package functions that I know one person in the class is interested in. Is there others? Are there folks in the class that are interested in like principal components analysis, also known as PCA? We can do that in vegan. We can do redundancy analysis, RDA. We can do canonical correspondence analysis, CCA. Any of this?
I'm interested in PCA.
Say that again, Ashley.
I'm interested in PCA.
PCA, very good. Okay. Others? Okay, well, we'll summarize the major functions, but then we'll spend time for sure in PCA and NMDS as we move through next week, if that sounds good to everyone. Okay, cool. Well, have a good weekend, and I'll see you. I'll see you next